the Euclidean metric, which goes dr squared equals dx squared plus dy squared plus dz squared. And what I'm going to do is express that as a inner product, which goes dx, dy, dz in a matrix form, and dx, dy, dz in a matrix form. And that's still dr squared, but this time it's represented as sort of a matrix. Let's change this though to an S. So because I want to use S in another, or I want to use R in another format, and basically I want to first express z equals r cosine theta, r equals r, or y equals r sine theta sine phi, and z and x equals r cosine, r sine theta cosine phi. And bear with me now, I'm going to calculate something that's called the Jacobian. And a couple of different notations for the Jacobian could be del x comma y comma z right arrow over del r comma theta comma phi down arrow. And that is going to be basically the right arrow means I'm going to go across del x, del y, del z, and the down, so del x, del y, del z, I'm going to repeat that 3 times. Del x, oops, don't have enough room on the screen. Okay, del x, del y, del z, and we're going to go del r, del theta, del r, del theta, del phi, del r, del theta, del phi, del r, del theta, del phi. Okay, so this is what the Jacobian is. It's basically taking all of these things. For instance, del x, del r is just going to be sine theta cosine phi. Del y, del r is sine theta sine phi. Okay, and so let's do del x, del theta. Del x, del theta, since theta is here, it'll be r cosine theta cosine phi. R cosine theta cosine phi. Okay, let's go into our Mathematica demo. This is my previous video. I figured out how to find the tangent to a circle, the tangent plane to a circle. So in this video, I want to look at the Jacobian of this thing, which is figured out. We're going to make a 3 by 3 matrix. Just going to go dun 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 dun, and it's going to be d of, okay, actually I confirmed that that one worked, so let's do it this way. Copy, copy, copy. Whoops, not control enter. Copy, 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 comma, copy, copy. Oh no, 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 no. Good idea, bad implementation. I'm gonna say we're gonna go X, Y, and Z across. I don't know if I did it across and down before. I should have done this first. And X, Y, Y, Y. Okay, yeah, going across. z, z, z. Okay, so that's going across, and then down I'm going r, theta, theta goes here and here, and then phi goes here, here, and here. And then let's make a, this is going to be our Jacobian, equals that, and so I'm going to say, matrix form of the Jacobian, so we can see that in a nice format. Jacobian. And symbol Jacobian is protected, so let's just call it Jake. And there we've got our Jacobian. Now, what can we do with this Jacobian? This is where earlier, what did we do? We said that the metric ds squared was equal to dx dy dz times dx dy dz, these two matrices multiplied together. How are we going to change that? Well, we're going to put in dx dy dz. Actually, we're going to put in dr d theta d phi, but then we're going to use our Jacobian matrix to fix it. So the dr d theta d phi is multiplied by something over del r, something over del theta, something over del phi, del x, del y, del z, going that way, del r, del theta, del phi. So del x, del y, del z, del r, del theta, del phi, del x, del y, del z. So dr times del x del r plus del theta times del theta del phi times del phi times del x del theta is what dx is. Dx equals del x del r dr plus del x del theta d theta plus del x del phi d phi. So this is essentially what you get from multiplying this by this first column here. And then dy is del y del r dr plus del y del theta d theta plus del y del phi del phi. So you can multiply that through on that second column. So this is equal to dx dy dz. And then this is going to be same thing, except that dx dy dz is over here on this side. And so you can just go, well, it's the transpose of this thing. So del x del r is still up there in the corner, but then we start going down del x del theta and del x del phi. And you can see del x del r times dx plus del x del theta times dy plus del x del phi times dz. Same thing in the next line, del x, del y del r, sorry, del y del r, del y del theta, del z del y del phi. Okay, so anyway, in the end, what happens is that we've got these two Jacobians, the Jacobian and the Jacobian transpose, and the end product is what is commonly known as sort of the metric. So let's go ahead and take our Jake dot transpose of Jake and see what comes out. Is it symmetric? It doesn't look symmetric just yet. It's pretty enormous there, but you can see some things like here we've got a cosine squared theta. Here we got a sine squared theta. Here we got a cosine squared theta phi and a sine squared phi. And those are both being multiplied by sine squared theta. So why didn't that simplify? Probably because Mathematica doesn't simplify unless you tell it to. So let's put simplify in there because there's no reason it shouldn't. And boom. 1, 0, 0, 0 r squared 0, and 0, 0 r squared sine squared theta. So what does that mean? That means that that huge mess that we had from the Jacobians can be represented as dx, dy, dz times dx, dy, dz is equal to dr, d theta, d phi times this mess. Whoops, it's going to block it. And then that is multiplied by dr, d theta, d phi. And then we'll have, that's going to come out to be dr times 1 times dr, so it's dr squared, plus r squared d theta squared, plus r squared sine squared theta d phi squared. And so that is something in Wheeler General Relativity Lecture 2sphere.pdf. It is the first equation on the page. ds squared equals dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So this article was sent kind of linked to from George Dishman, and so I'm going to read through it a little bit. The three-dimensional Euclidean. The easiest way to find the metric of the two-sphere, or the sphere in any dimension, is to picture it as embedded in one higher dimension of Euclidean space, then restrict to constant radius. So what he's going to do with that two-sphere is set r equals, big R equals constant, giving ds squared equals r squared d theta squared plus r squared sine squared theta d phi squared. And so dr squared is set to 0 here, so that disappears. And otherwise the large r's are replaced with big R, or the little r's are replaced with big R's. So something happened here, because at this point he actually invoked a matrix. This was literally equal to dx, dy, dz dot producted with dx, dy, dz. Now, can we still say anything about this? Because he's introducing a new two-dimensional metric, which, and so that was, yeah, that became dr d theta d phi 1 r squared sine theta. So what did he do? He's basically just eliminating that column and that column by setting dr equal to 0. So it's really still there, but this would be d theta d phi r squared 0, 0, r squared sine squared theta. And then, okay, so he's doing the inverse, and then this would be d theta d phi. Okay, what's the inverse of this function for? Well, presumably if we've got an inverse function, then what we had before was a mapping of r theta phi, phi to x comma y comma z. Now that was these equations right here. So what if we wanted to have x, y, and z and convert it to r, y, x, y, and r? Well, for one thing, r would be square root of x squared plus y squared plus z squared. X should equal r. Actually, let's start with z. Z is, let's see, we've got a circle, we got, z is right here, we got this angle, and that angle is theta. Z, I don't want z, I want theta. Theta is arc, let's see, z is sine, r cosine theta. Z over r, I want arc cosine. Arc cosine of z, because I don't want arc cosine of z over square root of x squared plus y squared plus z squared. Okay, and phi is going to be, could be expressed as arc cosine of, say, x over square root of x squared plus x over square root of x squared plus y squared. So that would give us a function of r, would give us r, theta, and phi in terms of x, y, z, x, y, z, and x and y. All right, so we got this Jacobian, and we've written it twice, del x, y, z, del r, theta, phi. Is that what I did down here? Yeah. And then it would be times del r, no, it'd be del x, del y, z again, but this time going down, del r comma theta comma phi, and that would go to the right. This Jacobian times Jacobian inverse, transpose, is equal to the metric. Now, this is something to confirm or something to test as far as I'm concerned. I'm not 100% confident, but it seems to be what Euler is saying right now, that this would be the inverse of del r theta phi del r theta phi del x y z del x y z, with this going that way, that way, that way, that way. Are these inverse metrics? I mean, are these reciprocal, what do you call them? Inverse metrics. And so I think I'd like to test that in the next video, if I can.